Here's the problem we're facing today. You want to play a game that requires a 15-sided die, but all you have in front of you is a regular, fair, 6-sided die. The key requirement is that every number from 1 through 15 must be equally likely to come up, just as if you had a real 15-sided die. So, our challenge is to figure out a way to use the 6-sided die, possibly rolling it multiple times, so that each outcome from 1 to 15 is just as probable as any other. We'll explore how to set this up, step by step, including the math and reasoning behind the solution. To make sure everyone's on the same page, let's clarify our setup. We have access to a fair die with 6 faces, numbered 1 through 6. Our goal is to simulate the roll of a fair 15-sided die, so results from 1 to 15, and each result must come up with exactly a 1/15th probability. The only constraint is that we are allowed to roll the 6-sided die as many times as we want in order to achieve this. Our approach needs to make use of this freedom. The core idea is to increase the number of possible outcomes by rolling the die more than once. Each time we roll the die, we're multiplying the number of possible sequences. For example, 2 rolls create 6 times 6, or 36 unique outcomes. So, in general, if we roll the die n times, there are 6 to the power of n possible result sequences. To simulate a 15-sided die, we need at least 15 possible outcomes. We'll look for the smallest n such that 6 to the n is at least 15, so we've got enough outcomes to map over the numbers 1 to 15. Let's see how this works in practice. If we roll the die twice, we create 6 times 6, or 36, possible, unique results. Each of these can be represented as an ordered pair, the result of the first die and the second die. The next question is whether we can map these 36 outcomes to the numbers 1 through 15 in a fair way, that is, whether 15 divides evenly into 36. Since 36 divided by 15 is 2 with some remainder, it doesn't divide evenly. That means after we've used 30 outcomes, 2 sets each per number from 1 to 15, we'll have 6 outcomes that don't map perfectly. Those leftovers will be important in the next steps. Here's how we proceed, step by step. First, we list all possible ordered pairs of 2 die rolls, giving us 36 distinct outcomes. Next, we assign the numbers 1 to 15 to these outcomes, doing so 2 full times since 15 times 2 is 30. This covers 30 out of 36 possible sequences. For the last 6 outcome pairs, we don't assign a number to them. They represent unlucky rolls. If a player rolls one of these, we simply disregard the roll and start over, re-rolling both dice. This process continues until the player gets one of the 30 mapped outcomes, and that outcome translates directly to a number from 1 to 15. In this way, each number from 1 to 15 has exactly 2 out of 36 chances in every try. And since 2 divided by 36 is 1 divided by 18, but since we retry on leftovers, the actual probability normalizes to 1 divided by 15 for each outcome. To keep things precise, here's a method for encoding each 2-dice roll as a unique number from 1 to 36 dice got. Take the result of the first die, subtract 1, multiply by 6, and add the result of the second die. For example, if you roll a 3 and a 5, the calculation would be 3 minus 1 times 6 plus 5. That's 2 times 6 is 12, plus 5 is 17. So the roll, 3, 5, maps to outcome number 17. This ensures each sequence is mapped clearly to a distinct number from 1 through 36. Now, let's talk about why this method is fair. Since the die is fair, every roll is independent, and each pair is equally likely. By discarding the final 6 outcomes that don't map to any number, we remove them from the pool. But only when they occur. They don't bias the results. Whenever the process does deliver a number from 1 to 15, each has exactly 2 corresponding pairs out of the 36, and no number is favored. The process of discarding and re-rolling when an unassigned outcome appears means that, over time, each outcome 1 to 15 will come up with precisely equal likelihood. This approach is called rejection sampling, and it's a standard statistical technique. Let's analyze the efficiency of this method. Each attempt, meaning 2 dice rolls, has a 5/6 chance of producing a valid outcome since 30 out of 36 pairs are mapped to 1/15. Statistically, the expected number of attempts before success is 1 divided by 5/6, which equals 6/5, or 1.2. Each attempt uses 2 die rolls, so the average total number of die rolls to produce a valid number is 2 times 6/5, which is 12/5, or 2.4. So, most of the time you'll get a result after just 2 dice rolls, and sometimes it may take a little longer if you hit a rejected outcome. The intuition here is that we're leveraging the uniform randomness of multiple 6-sided dice rolls to create a larger pool of outcomes, and then mapping this larger set fairly onto our 15 possibilities. By using rejection sampling, we avoid introducing any bias, because we only accept sequences that fit evenly into our desired range. It's efficient, it's mathematically sound, and it's a great example of creative problem solving with randomness. This approach applies more broadly in simulations. When you need to generate a fair outcome from a small set, you can often achieve it by combining several random events and repeating as needed. To wrap up, here's the method in a nutshell. Roll a fair 6-sided die 2 times, then encode each ordered pair as a number from 1. Assign the numbers 1 to 15 to these pairs, 2 times each for a total of 30 assignments. If you roll one of the extra 6 pairs that aren't assigned, simply throw away the result and try again by re-rolling both dice. This guarantees that each number from 1 to 15 is just as likely as any other. Exactly what we needed to simulate a fair 15-sided die using just a regular 6-sided one. Thanks so much for joining me as we tackled this classic Janet Steet quant interview question. I hope you found the step-by-step reasoning helpful for understanding how to simulate one kind of fair random process with another. If you enjoyed this video and want more fun and challenging problems broken down in a clear and engaging way, be sure to subscribe to the channel and hit the notification bell. And if you're looking for more deep dives and resources in math, statistics, and probability, don't forget to check out datalooper.com. See you in the next video.